Recording started.
Hi, this is Steve Ruff. I'm a Mars geologist at the School of Earth and Space Exploration at Arizona State University, and I'm here today to give you an overview of the geology of Mars. So the first thing to talk about here is the difference between Earth and Mars, some of the differences anyway. And one of them is that Mars is quite a bit smaller than the Earth. As you can see from this picture, it's maybe a third of the size of Earth. And it's also farther away from the Sun than the Earth is. We use a unit of measure called an astronomical unit. Earth is 1 astronomical unit from the Sun, which is about 93 million miles. And Mars is about 1.5 astronomical units, so it's about 140 million miles from the Sun, and that means it takes longer to get around the Sun. So a Mars year is about a little less than 2 Earth years, so it takes a little less than twice as long to get around the Sun as Earth. But coincidentally, the length of a Mars day, which is called a sol, is about 1 Earth day. It's actually 24 hours and 39 minutes, which is really just a coincidence because none of the other planets have a day that's similar. Rotation on its axis is a day. So that 1/3 size of the Earth means that the gravity of Mars is actually about 1/3 of Earth's gravity. So you would actually weigh 1/3 of your weight on Earth if you were on Mars. Mars does have an atmosphere. It's very thin though, and it's mostly CO2 rather than nitrogen and oxygen like on the Earth. And the pressure, the atmospheric pressure of Mars is only about 1% of the Earth at the surface. So it's a very, very thin atmosphere and mostly CO2, so you couldn't breathe it if you were there on the surface. So those are some of the differences. But let's now move on to how the exploration of Mars began. And before there was telescopes, all we could do as humans is look up into the night sky and see a little red dot. But with the advent of telescopes in the 1600s, there was astronomers who began to turn those telescopes to Mars and look for different features. And Galileo was really the first astronomer credited for looking at Mars through a telescope, and he was looking for the phases like the Moon has phases and Venus has phases, but Mars, it's really difficult to see those. And other astronomers using telescopes were able to see surface features. They could document how long it took for those features to come in and out of view, and they could figure out that Earth or that Mars sol, that length of a day. And they were very close, even back then with their primitive telescopes. And they could also see that there were polar caps and clouds, so they knew there was an atmosphere, for example. But that was using telescopes, and really the first, actually, I'll describe some more of those observations in the 1800s as the telescopes got better. Some astronomers, like an Italian astronomer named Schiaparelli, could see with his telescope features on Mars that looked like these lineations, these lines that sort of roam across the surface of Mars. And he thought that those lines could perhaps be some kind of channels on the surface of Mars, and he didn't talk about whether they were man-made or natural channels, but he used the Italian word canali for channels. And there was an American astronomer named Percival Lowell in the late 1800s who built a telescope in Flagstaff, Arizona, to look at those, what he thought were canals. And so he mapped these canals using his telescope and his eye at that telescope. And so this was a period of time when the telescopes really weren't good enough to see features, and these astronomers really were probably being deceived by what they were seeing through their telescopes. But at this time, in the late 1800s, the idea that there were canals on Mars made it sound like there were intelligent creatures on Mars that were, in this case, maybe trying to move water from the polar caps of Mars to the equator to bring water. And so it was also at this time that Mars mania really began, and it was sort of moved along by authors of the period. And H.G. Wells' War of the Worlds is a classic example of the Mars mania, where not only was Mars a place inhabited by intelligent creatures, but they might actually want to come and take over the world. So there was a real different view of Mars at the turn of the last century than what we understand today. So it was during the 1960s that we could finally begin to really explore Mars in a way that we couldn't using earthbound telescopes. And so in 1969 there was this was the second set of spacecraft to fly by Mars, and they were equipped with cameras, and they took a few dozen images, and the resolution of about 300 meters, that's about 300 yards or so. And some of the first features that were seen by those spacecraft on Mars, as features on Mars, were craters. This was something that is not observable with telescopes from Earth, certainly not the ones that were available in the earlier era of exploration. So craters on Mars was a surprise, and this looked an awful lot like the Moon, and so this was really kind of a shock to the scientists of the day, where it wasn't expected to be such a lunar, such a moon-like place with all of these craters. And in fact, later missions to Mars, later spacecraft, and with color cameras in this case, showed the surface of Mars to have many, many craters. They tended to be limited or dominating the southern hemisphere, the so-called southern highlands, have many more craters than the northern plains. But nevertheless, it shows that Mars has suffered impacts from meteorites just like the Moon has. And so when you see the Moon's cratered surface, and occasionally there's craters that are preserved on Earth, it shows that Mars is no different. It has seen meteorite impacts just like other bodies in the solar system. But fortunately for geologists, Mars has many other interesting features in addition to the craters. So Mars really is a planet of volcanic features and volcanic processes. So here's a sort of distorted global view of Mars, kind of stretched out so you can see the whole of Mars on a single single image. And these yellow arrows point to volcanoes on Mars that are actually so huge that they're visible from orbit. Earth has many volcanoes, and some of them are pretty big, but typically they aren't big enough to be seen from a distance like these are. And in fact, one of the volcanoes on Mars that I'll show in the next slide here is called Olympus Mons. This is the biggest volcano in the solar system. This could easily cover most of the state of Arizona, and the height of it is 3 times the height of Mount Everest. So this is a huge volcano, and it was built up slowly over millions of years by what we can see in this much narrower view of the volcano. This shows lava flows, these sort of streaky features going up and down. They're coming from the top and flowing downward, and you can see what are called levied channels. So levees, like you might see on a riverbank, also form on volcanic lava flows. And these kind of lava flows typically, this is showing that they're very runny flows. They're very low viscosity flows, like you'd see in Hawaii. So we can sort of deduce something about their composition, that they're basaltic lava flows like you'd see in Hawaii because of this low viscosity character. So Mars also has canyons like Earth, but unlike Earth, these are the biggest. Well, they're the biggest canyons in the solar system occur on Mars. So the black box shows right next to some of those volcanoes is a huge canyon system that, if it were on Earth, it would cover the whole of the United States. So this is a canyon system unlike any on Earth purely because of its size. So this is a huge canyon. And the next slide shows a closer up view. It's called Valles Marineris, and this is just a portion, the main portion of this huge canyon on Mars. And if this were on Earth, it would stretch from Los Angeles to St. Louis. And so this is a huge canyon that was formed by a combination of tectonic processes, faulting and rifting of the crust of Mars, followed by and including landslides. We call it mass movement. So landslides erode and rifting and earthquake kind of processes, Mars quakes, opens this thing up and subjects it then to landslides afterwards. So huge canyons on Mars. There's also channels on Mars. Now channels on Earth, these are actually not like the channels that were being seen supposedly by those earlier astronomers. These are what we call catastrophic outflow channels. They're really unlike, there's really nothing quite like it on Earth. These are channels that have formed as we really think it's water. There was debate for a while about whether there was some other process that could form these, but it's really been settled pretty clearly that these are flows of water that seem to start out of nowhere. So the starting position in this image is simply a place where the land seems to have failed catastrophically. It's collapsed, and out of that collapsed area, water has emerged and flowed to the right in this picture for more than 190 miles, and it flows off into a trough off to the right side of this picture. So huge channels formed from catastrophic outflow of water, and it's still kind of a mystery how that happens. Probably some kind of ground ice that melts rapidly in some way, but it's still quite a mystery actually. The next slide shows sort of a closer up view and just shows how big these channels are. And this is just the width of a series of channels from these catastrophic outflows, and you can see at the top of this scene what looks like this collapsed area, and more water emerged, and the water comes out very rapidly and it scours the terrain and makes these streamlined features, these streamlined islands and other streamlined flow features really show the power of that water as it scours across the surface of Mars. The next slide shows that Mars is not just volcanic rock, igneous rock, and volcanic features. There are places on Mars where huge stacks of sedimentary rock have accumulated. So here's a crater called Gale, and inside that crater is a huge stack about 3 miles high of eroded sedimentary rock. So this was a crater that was filled up with sedimentary material that turned into rock, and now it's being eroded away. So we can see, actually I'll zero in on a little feature. There's within this stack of 3 mile high sedimentary rock is a canyon, and within that canyon you can see beautiful layers of sedimentary rock. So you can see the nicely layered cliff face here, and just to give you a sense of scale, this is a huge cliff face. So the Empire State Building gives a sense of that scale. So this is not just a little road cut. So layers of sedimentary rock have piled up in places on Mars, and it's still kind of a mystery what these sediments really mean. Are these ash deposits from volcanoes? Are these wind-blown sediments? Are these sediments that formed, that accumulated in a lake? It's still unclear, and in this case, though, we're going to have the opportunity to find out. The next rover going to Mars is going to Gale Crater, and it's going to look at these sedimentary rocks and hopefully give us answers about what process or processes have formed these huge mounds, these huge piles of sedimentary rock on Mars. Now, in addition to sedimentary rock, there's all sorts of sedimentary material in the form of loose sand that blows around on Mars and makes incredible dune fields and individual dunes all over the planet. So, you know, Mars really has all sorts of dune features that, and you know, they're called ripples, they're called dunes, and so the action of wind on Mars is very dominant. In fact, it's sort of the dominant way that material on Mars is transported and eroded. The wind does erosion and transport, compared to Earth, where water really does most of the erosion and transport. Mars, the winds are doing that. Even with that very thin atmosphere, there's enough wind, enough air to do these kind of to do these processes of blowing sand around. The next slide shows just a close-up. This is about a little less than 2 miles across. This is just an example of how beautiful these dunes can be. They're made out of basaltic sand in most cases, so they're very dark, dark sort of basaltic sand dunes. And just for scale again, if this were on Earth in Egypt near the Great Pyramids of Giza, which I'm showing, those are basically to scale. You can see just how big some of these dunes on Mars could be. They would easily swallow up the Great Pyramids of Egypt if they were in that location, which of course they aren't. The next set of slides talks about ice on Mars. So Mars does have water today. Most of it is in the form of ice, and a lot of it is in these polar caps. So even the earliest astronomers could recognize these bright features at the North and South Pole. And actually, this is a Hubble telescope image from Earth's orbit. So this is a really fantastic view. And you can see the light and the white-colored features. Now, some of the stuff that you see in white is actually water ice clouds. So Mars does have some ice in the form of little crystals in the atmosphere that form clouds. I'll first zero in on a canyon in the North Polar Cap. And here's a close-up view. And this is a canyon called Chasma Boreal that has eroded into these North Polar Cap deposits. Now you can see how finely layered these deposits at the North Polar Cap are, and we think it's a combination of water ice and dust and probably some CO2 ice. So Mars gets cold enough that CO2 in the atmosphere can actually precipitate out. It can turn into frost and make dry ice. So these caps in both cases are some combination of water ice and CO2 ice as well as dust. And you can really see the beautiful layers, and then there's some dunes off to the right in that canyon. The South Polar Cap is smaller, but it has similar sort of characteristics. Now these are the permanent caps that hang around all year long. During the Martian winter at both poles, especially the South Pole, this whole area would be covered in CO2 frost. But this is the cap that remains, the residual cap. And just for a sense of scale, although it's smaller, it's still a very large feature. And coincidentally, it's about the size of Iceland here on Earth. And I couldn't resist including this just for that comparison. But what's very unusual about these caps is, in this case, the South Polar Cap has these strange, very strange pits that form. We call them Swiss cheese for obvious reasons, and you can also see some vague little features. We call them polygonal terrain. And we think that what's happening here is that it's some combination of collapse of the CO2 as it sublimates, as it evaporates essentially into the atmosphere, and it creates these collapse pits that show that Mars is probably going through climate change right now. These pits are forming today and they're expanding today. We can see that happening when we take pictures from one season to the next. And so this is an indication that these polar caps are in a state of change. So Mars climate is changing. Now the last thing I want to talk about is another example of ice on Mars. And this is a global map from an instrument called the neutron spectrometer, and it's able to measure different elements on Mars. And in this case, it's a map of the element hydrogen, and blue shows places where there's more hydrogen. And in those blue areas, there's so much hydrogen that really the only thing that can account for all that hydrogen is H2O in the form of ice, so water ice. There's no minerals that could have this much hydrogen, so it's very likely ice. And so several years ago, a mission was sent to the northern latitudes of Mars, to one of these places that looked like it might have this buried underground ice just a few inches below the surface. And so here's a picture, a computer picture and a computer graphic of this Phoenix lander descending to the surface with these rocket thrusters. And the next slide shows an actual image underneath that Phoenix lander, and it shows what no one expected, that those retro rockets on that lander were able to blow away a few inches of soil and expose the ice. So the white, very bright features in the middle of this scene are actual, it's this ground ice that we could see from orbit with this neutron spectrometer. Sure enough, is just below the surface, just underneath this Phoenix lander. And it was really a remarkable discovery, and it really shows that these high latitudes of Mars have ground ice just below the surface. We call it permafrost, like in the Canadian Arctic. And so my last slide is a summary. And the idea that Mars geology is dominated by volcanic rocks and processes should be apparent from what I've been able to show you. So this is a volcanic planet for the most part, but there are some sedimentary rocks that we can find. It's still, in some cases, a mystery where those sediments came from, how they were deposited, and whether or not they are an indication of water, sedimentation in water. But we hope to find out with the Curiosity rover, the next rover that's going to arrive about a year from now, August of 2012. And although there are examples of water erosion like those channels, most of the erosion and the change on Mars is due to wind rather than water. So it's unlike Earth, where water is dominant. On Mars, the wind is doing most of the change and erosion. And the water that we find today on Mars is mostly in the form of ice at the poles and in permafrost at the high latitudes. But there are suggestions in some other images that I haven't shown you of liquid water today. But Mars is such a cold and dry place that the water really would be present as ice in most cases rather than liquid water. So that's it. I hope you've learned something about Mars, and I've enjoyed telling you about it. So thanks a lot for your attention.